So, you are learning limits for the very first time, maybe in your precalculus class or your calculus class. I think this is the best way for you to see, for you to understand, and for you to get a feel of what a limit is. We are going to use the table of values to determine the limit of a function when x is approaching certain value. We are going to go over 6 examples to help you understand. First, we are going to have the limit as x approaching 2 of this function. So, on the bottom I set out a table already, but we should always plug in this number into all the x's and see what happens. So we will have 2 squared minus 4 over 2 squared minus 3 times 2 plus 2. On the top we get 0, on the bottom we also get 0. So we have 0 over 0, but we cannot draw any conclusion for limits. What we can say right here is that when x is exactly equal to 2, this right here is undefined because we have a 0 on the bottom. So we'll just put down UND stands for undefined. Well, that's not the answer for the limits though, because when we are talking about limits, we don't care about when x is exactly at this value 2. We care about what will happen when x is around 2, when x is approaching 2. Now, let's think about it. If you look at the number line, here is 2. We have 2 directions of approaching 2. One is we can come from the left. The other one is we can come from the right. Let's focus coming from the left first. So, let's just think about some numbers so we can get closer and closer to. Maybe we are at 1, but that's a little bit too far away. Well, okay, how about 1.5? It's still too far away, right? How about 1.9? Now we are talking. How about 1.99? Sounds really good. And that's exactly what I'm going to put down right here, 1.99. But can we get even closer to 2 than 1.99? Sure thing, 1.999. Well, 1.997, up to you, right? Okay, this is good, but can we even do better? Yes, 1.9999. And of course, continue, but I think this is enough. And let's take a look of what will happen if you just plug in 1.99 into all the x's. And now this is legitimate because x is not exactly equal to 2, right? So, when you plug in 1.99 into all the x's, I have the answer for you already. We will get 4.0303. Okay, then how about let's try 1.999. Okay, go ahead and plug that into your calculator. We will end up with 4.0030. Pretty good. Now if you get even closer to 2, we have 1.9999. We will end up with 4.0003. Okay, as you can see, these numbers are getting closer and closer to what? To 4, right? So right here what we can say is that the limit as x approaching to 2 from the left hand side, so we put down a little negative, meaning it's like you come from like a smaller numbers and you are increasing up to 2. Of the function, I'm just going to put down f of x. This right here, we can see that's approaching to the number 4. Okay, that's pretty good. But we will also have to check the other direction when we come from the right. Okay, so that means a number bigger than 2 first, maybe as 3. But that's too big, of course. How about 2.5? We can do better than that. How about 2.1? Sure thing. How about let's try 2.01? Okay, now we are talking. Can we get even closer to 2? Sure. 2.001. Aha. And then let's also try 2.0001. Great. Now the rest is just enter these values into your calculator. When x is exactly 2.01, now notice again this is legitimate, we can plug that into the function. We will end up with 3.97 and then 0.3. Okay, next, when we plug in 2.001, we will end up with 3.997. Continue, we will get 3.9997. Okay, this is interesting because as you can see, these output of the function, right, this y value of the functions, they are closer to what? They are getting closer and closer to 4 as well. Right here, based on this, we can write the limit as x approaching 2 from the right hand side, meaning a bigger number than 2 and then getting smaller to 2 for the function, and then we can conclude that it's equal to 4. Now, as you can see, when we have x approaching 2 from both directions, the y value, they are both approaching to 4. So we can say the limit as x approaching to 2, right here, of this function is just equal to 4. And that's the idea. So right here, the idea is really that you have to know what x approaching 2 means, and then set out a table of values, and then just see the behavior of the function when x is approaching 2. Alright? Now let's try another example. So here we have the limit as x approaching 9 of this function. Let's go ahead and plug in 9 to all the x's. Well, the top is square root of 9, which is 3. Minus 3, we get 0. On the bottom, we also get 0. So once again, we have 0 over 0. So that means when x is exactly 9, the value of the function is undefined. But we have to do more work in order to figure out the limit. Now, x approaching 9, we have two directions. So let me write that down. Here is 9. We can count from the left. So maybe start at 8, but that's a little bit too far. How about 8.5? Still too far, right? How about 8.9? Pretty good, but we can do better. Let's try 8.99. And then let's try 8.999. Pretty good, huh? And then 8.9999. Okay, and then I'm just going to plug in the x value into the calculator. We will have 0.1667 and then 0.16667, and then this is 0.16667. So what's the fraction for 0.1? It looks like 6 forever, right? After the 1. The answer is 1 over 6. So we can conclude that the limit as x approaching 9 from the negative direction or from the left hand side of our function, this is 1 over 6. But we will also have to check from the other direction. So coming from the right, maybe at 10, but that's too far away. 9.8, 9.5 I mean, still too far away. How about 9.1? Pretty good. How about 9.01? Good. 9.001? Better. 9.0001. We are talking. So let's go ahead and plug these values into the calculator. We will get 1.6662, and then we will have 1.6662, and then 1.12345, and then 2. Here we can say the limit as x approaching 9 from the positive direction of our function is 1 over 6. Now again, they are equal, so we can conclude the answer for the limit. It's actually 1 over 6. Next, let's try this one-sided limit. We have the limit as x approaching 2 from the positive direction, and we have 3 raised to the 1 over x minus 2 power. So still, let's plug in 2 into the x. We will have 3 raised to the 1 over 2 minus 2, and that's 3 raised to the 1 over 0. Because we have 1 over 0, well, when x is exactly 2, the value of the function is undefined. Alright, done because of the 1 over 0. We cannot have 0 on the bottom when we're talking about computation. But for the limits, we have to do some work to investigate. So what can we do though? This time we are approaching 2 from just the positive direction. So let's see. I can go like this, right? So maybe start at 3, but that's too far away. Let's try 2.5. Again, too far, so how about 2.1? And so on, right? In this case, I'm actually going to start with 2.1. You guys will see why. And then 2.01, and then 2.001. Now, if you enter 2.1 onto your calculator, this is manageable. You will have 59048.99 something, right? Okay, next, if you plug in 2.01 into the X here, let me tell you, your calculator might not be able to handle it, but you will get about 5.15. And if your calculator returns this, capital E 47, this just means that we have multiplied by 10 raised to the 47th power. So it's pretty much like saying we have 5 and then 47 zeros after that, which is a really big number. And I'm pretty sure if you enter 2.001 on your calculator for this, it's going to either show you overflow or maybe some of the calculator will just tell you infinity. So let me actually do the question like this. I am just going to be plugging 2.1 into just this part right here, right? And then I'll work that out for you guys, just the exponent part. So we will have still the base 3, but 2.1 into the x. It's like this, 2.1 minus 2, right? And then you have 1 over 0.1, which is just 10. Okay, that's the idea. And then if you plug in 2.01 into the x here, then similarly, let me erase this, you will end up with 3 raised to the 100th power. Okay, and then if you plug in 2.001 into just the x here, and then work that out, don't work out the 3 though, you end up with 3 to the 1000th power. So as you can see, when we are getting closer and closer to 2 from the positive direction, what's going to happen for the y value? It's getting bigger and bigger and bigger, right? So we say the limit for this right here is going to be infinity because the y values are getting bigger and bigger and bigger without any boundary. Next, let's try the same question, but the limit as x approaching 2 from the left-hand side. So just like what we did earlier, when x is exactly 2, this would be undefined. But not about the limit though, be careful. This time we are approaching 2 from the left-hand side. So you go like this, right? So maybe you can start at 1, and then 1.5, 1.9, and so on. Let's go ahead and use 1.9, and then 1.99, and then 1.999. This time we are going to run into a similar situation, but not that we are going to get infinity. You will see. When you plug in 1.9 into the whole thing, we will end up with 0.0000169. So it's a pretty small number. Next, if you plug in 1.99 and work out the whole thing, your calculator may just give you a 0, or you will actually get 1.94 times 10 to the negative 48th power, which is a very small number, right? It's a tiny number. So let's work out just the exponent without 3 to that power. So here's the deal. If you put 1.9 into just that part, don't work out 3 to that power, you will get 3 raised to the negative 10. Next, if you put this into just that, you will end up with 3 raised to the negative 100. And then same thing for the next one, 3 raised to the negative 1000. So as you can see, the y values will be smaller and smaller and smaller, approaching 0. Another way to look at it is that this is the same as 1 over 3 to the 1000th power, which is like 1 over a huge number, which is going to be tiny, right? Approaching 0. So the answer for this right here, it's 0. Okay? Now, here's one thing I want to point out before we go to the next question. If the question is asking us the limit as x approaching 2 without plus or minus, just a 2, and then 3 raised to the 1 over x minus 2 power, Well, in this case, we will have to check both directions. So, by what we did earlier, the limit as x approaching 2 from the positive direction, this right here will give us what? It was infinity, right? So this right here is equal to infinity. And from what we did earlier, the limit as x approaching 2 from the negative direction, 3 to the 1 over x minus 2 power, this was equal to 0. Now as you can see, the right and left limits, they are not equal. So if this is the question, then you have to answer it as the limit does not exist. Because the left and also the right limit, they are not equal to each other. Therefore, the limit as x approaching 2 does not exist. Okay, next, let's take a look at the limit as x approaching 0 from the positive direction, aka from the right hand side. And here we have sine of 1 over x. So let's plug in 0 into the x. We will get sine of 1 over 0, but 1 over 0 is bad, it's undefined. So that means when x is exactly 0, the value of the function is undefined. But not for the limits though, we have to investigate a little bit more. But before you do anything, make sure your calculator is in the radian mode because we're working with sine function. Anytime we work with trig functions in calculus, use radian mode. Okay, here we are approaching 0 from the positive direction. So it's like this. So we can start at 1, but that's too far. 0.5, still too far. How about 0.1? Yeah. So this time, let me put down 0.1 here, and then let's get even closer, closer, and closer. And then use a calculator. This time, you're going to see something weird, but let me just walk through this with you guys. First, when you enter 0.1 into the function, we will get negative 0.5440. Okay. Next, we will get negative 0.5064, approximately speaking. So right now you might be thinking, maybe the answer is just like negative 0.5, right? But not so fast, because when you plug in the next value here, 0.001 into the x, you are going to get positive 0.8269. I'm not kidding. You guys can go ahead and try it. So what's happening? Well, let's do one more, right? 0.0001. You will get negative 0.3056. So, if you look at the behavior of these values, are they approaching a certain value? Here, it's no, right? They are not approaching any particular y value. So, unlike what we have done before, that you guys can see that they all behave kind of nicely, but not this one, right? So, the limit as x approaching 0 from the positive direction, this right here, it's actually D and E does not exist. It is possible when we have a one-side limit and you still don't have the limit for that. Now for the last one, we have the limit as x approaching infinity. What does that even mean? Well, it just means that x is getting bigger and bigger and bigger without any boundary. Okay? So can we plug infinity into all the x's? Well, let's have a look. That would be 1 plus 1 over infinity raised to the infinity's power. Okay? And maybe some of you guys recognize this from earlier. 1 over infinity, that should be approaching 0, right? Because 1 divided by a huge number is just a super tiny number. I agree. So we should just be getting 1 plus 0 and then raised to the infinity's power. And then 1 plus 0 is just 1 raised to infinity, right? So shouldn't the answer just be equal to 1? Well, not so fast, because this thing right here, it's another indeterminate form. Just like the 0 over 0 situation that we have encountered in the first few questions. When we have 1 to the infinity's power in the limit situation, we cannot draw any conclusion yet unless we do more work. It's not equal to 1 in this case though. So, how are we going to do it? let me show you. Firstly, I'm just going to be plugging a big number. Let's say 100. But we can do better. Let's put maybe 1,000. I know. Let's actually just go big or go home, right? How about let's put 100,000. Okay, that's pretty good. How about the next one? Let's go even bigger. Let's do 1 trillion. 1 with 9 zeros. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so let's see what will happen. When we plug in the 100 into this expression here, use a calculator, you actually can work this out. You get 2.7048. And then if you plug in 1,000, you will get 2.7169. And if you continue plugging 100,000, you will get 2.718268, and so on, so on, so on. And if you plug in 1 trillion, you will get 2.7182822052. Let's have a look a little bit. As you can see, I plug in 1 trillion already, but this number, it's pretty much the same as that, right? So we can see that, in fact, when you plug in a bigger and bigger number, the y value is actually just approaching to about this number, about 2.71828, and so on, so on, so on. So in fact, I will write this down for you guys. When we continue, and if we go to infinity, some of you guys might recognize this number already. It's the special number e in mathematics. So in fact, the limit as x approaching infinity for this function here, we get e. And e is approximately 2.71828. So as you can see, earlier we got 1 to the infinity's power, but we didn't get 1 for the answer, because 1 to the infinity's power is an indeterminate form for limit, just like the 0 over 0. But isn't that 1 to any power just equal to 1? Well, let me explain. The reason that it doesn't apply here is because this 0, it's not exactly 0. Agree? Because it's from here. It's 1 divided by infinity. It's approaching 0, but it's not exactly 0. So this 1 that we see right here, it's not exactly 1. Therefore, it doesn't apply. So have a look right here though. What do I mean by not exactly 1? Let's take a look at the 1,000 right here. If you plug in 1,000 into the x, right, we will get 1 plus 1 over 1,000 raised to the 1,000's power. This right here is what? It's 1 plus 0.001 raised to the 1,000's power. So as you can see, we have a tiny bit after the 1, and then we have then is 1.001 raised to the 1,000's power. This right here gives us approximately 2.7169. That's why earlier 1 to the infinity's power, we have to be careful. I would say though, it's just a bad notation. People just put a 1 to the infinity's power. We really have to understand that the base 1 here is not exactly equal to 1 because we have the additional thing right here.